Hello and welcome to section 8.2, Integration by Parts. This is going to be the first new material for this course. So integration by part is going to be our first integration technique that we will see. So previously, and by previously I mean in Calc 1, you saw integration by substitution. Integration by substitution is normally abbreviated U substitutions. And integration by substitution was the opposite of the chain rule. It undoes the chain rule. Here, integration by parts which we will abbreviate IBP, integration by parts, will be the opposite of the product rule. So this will answer how you undo the product rule. So a slight derivation, so you kind of see where this comes from, and it's very quick. We start with the product rule. So the product rule says the derivative with respect to x of the product f of x g of x equals f prime of x g of x plus f of x g prime of x. Integrate both sides. And how are you going to integrate both sides? It's not how you spell sides. You're going to use the fundamental theorem of calculus. So if you integrate the left-hand side, the fundamental theorem of calculus says that the integral and the derivative just cancel. So you're just going to get the f of x g of x equals the integral of f prime g dx plus the integral f of x g prime of x dx. Rearranging this, we get the integration by parts formula. The integration by parts formula is going to be highlighted. 1 second. Integration by parts formula says if you are given differentiable functions f and g, then the integral of f of x g prime of x dx is f of x g of x minus the integral of g of x f prime of x dx. That is quite a mouthful. My dogs are barking. So the standard way of denoting this is by letting u equal f of x and v equal g of x. Differentiate both of these and we get du equals f prime of x dx and dv equals g prime of x dx. So we get the standard integration by parts formula. The integral of u dv equals uv minus integral of v du. It's in blue, which means you need to know this. Best way, it's a mouthful still. So best way of seeing this in action to see it's really not that bad. It's not as intimidating as it looks. Let's just do an example. So evaluate the integral of x cosine x dx. So looking at this, you can't just straight integrate it. You can't do a u substitution because there's nothing to substitute that would get rid of all of the variables. So we're going to use integration by parts, and it's especially obvious because we have a product of two functions, so integration by parts. So product of two functions, and it's not how you spell functions, means we're going to use integration by parts. Okay. To do integration by parts, we define u and dv in our little integration by parts formula. And we generally let u be the term that terminates. And by that I mean terminates after differentiating it multiple times. And then we let dv equal what is left, and it's normally the thing we can integrate. So looking at this, if we let u equal cosine x, the derivative of cosine x is negative sine. The derivative of negative sine is negative cosine. Derivative of negative cosine is sine. Derivative of sine is cosine. So it's a loop. So we don't want u to equal cosine. So instead we're going to let u be the other thing. So let u equal x. And it's pretty obvious. If you integrate it once, you get 1. Integrate it again, you get 0. It terminates. Terminates pretty quickly. If u equals x, then dv equals what is left over, so cosine x dx. And the integration by parts needs du and v. So we're going to find du, and we're going to find v. Du is just the derivative of u, which is 1 dx. So it's just dx. And then v is the integral. So we're going to integrate. Integrate dv and differentiate u. Integral of cosine x is sine x. So the integral of x cosine x dx equals uv minus the integral of v du, which, using the notation that we have, or the way that we defined u and v, that is x sine x minus the integral of sine x dx. Now, it doesn't look like we did much because we integrated x cosine x and we got an integral back out. However, this integral is something we can easily integrate. So this is x sine x minus the integral of sine is negative cosine. So that's plus cosine x and then plus c. And then you're done. So the way you do integration by parts is you define your u and dv, you differentiate u, integrate dv, and then just plug it into the formula. Notice, however, as I mentioned, that the choice of u matters. I kind of mentioned it. So if we switched it, and by that I mean if we said u was cosine x, dv was x, differentiate u, you get negative sine x dx, integrate dv, and you get v equals x squared over 2. First off, it's already ugly. But if you were to plug this into the integration by parts formula, you'd get u times v, which is x squared over 2 times cosine x, minus the integral v du, so minus negative x squared sine x over 2 dx. And this last integral is more difficult to integrate or evaluate. It went from having a simple x to having a complicated x squared. So our choice of u was wrong. So to help remember or figure out what to let u equal, remember u, I said u, I'll say I use Liotti. So Liotti, this is L-I-A-T-E. L stands for logarithms. I stands for inverse trig. A stands for algebraic. So algebraic as in x squared, x cubed, square root of x, etc. T stands for trig, and E stands for exponential. Exponential as in e to the x, a to the x, etc. All right, so, I mean, cool. You remember Liotti. What does this mean? If you read this left to right, so in the order Liotti, the first expression to appear in the integral should probably be u. I say probably because it's not always true, but for the most part, this trick works. So example, we will evaluate the integral of natural log of x dx. Okay, looking at this, we don't know the integral of natural log of x. So we have to do a u substitution or integration by parts. There's nothing to substitute, so we're not going to do a u substitution. But it also doesn't really look like you want to do integration by parts because there's not a product of two functions. Well, that's not entirely true. Integral of natural log of x is the same thing as the integral of 1 times the natural log of x dx. 1 is an algebraic expression. It is 1 times x to the 0. And natural log of x is a logarithmic expression. So when looking at Liotti, we have L, I, A, T, E. We have L and we have A showing up. So we want to let u be the first one to appear, which would be L. So we want u to be natural log of x. And then dv is what is left over, which in this case is just dx. So logs come before algebraics. So we're going to let u equal log. Okay, differentiate u. You get 1 over x dx. Integrate v, dv, you get v equals x. And then you have the integral of natural log of x dx is uv, which is x, natural log of x, minus the integral of v du, which is x over x dx. Well, that is exactly x natural log of x minus the integral of dx, which is x natural log of x minus x plus c. Okay. So, when in doubt, use Liotti. When in doubt, add a 1. Won't always work. It really only works for natural log. Not entirely true, but for the most part. But key thing here is Liotti. So this is great. We get an integral that we can't integrate easily, turning into an integral that we can easily integrate. But we're not always going to live in fantasy la la land. Sometimes, after applying integration by parts, you might not get an integral that you can solve or evaluate. So what do? So do integration by parts again. So let's see an example. We're just going to string a bunch of integration by parts together. So let's evaluate, I need an integral sign, integral of x squared sine x dx. So why don't you pause this and integrate, try this on your own. After you do integration by parts one time, the integral you get, you can't just immediately solve. You should recognize that you can do integration by parts again, but you should get an integral that we've done in this section if you did your first integration by parts correctly. Okay, so when doing this, we have Liotti. So we do not have logarithmics, we do not have inverse trigs, we have an algebraic, we have a trig, and we do not have exponentials. So we have algebraic and trigonometric. So we want u to equal the algebraic expression, which in this case is x squared, and dv to equal sine x dx. Differentiate, you get du equals 2x dx. Integrate, you get v equals negative cosine x. So the integral of x squared sine x dx equals uv, which is negative x squared cosine x, minus the integral of v du, which is minus the integral of negative 2x cosine x dx. And let's just clean that up a little bit. That's minus x squared cosine x plus 2 times the integral of x cosine x dx. So we now need to integrate x cosine x, but this is nicer than x squared sine x because we have 1 power of x instead of 2. So it looks like we were on the right track. So you didn't choose incorrectly for u. Looking at this is the first example that we did, so I'm going to go a little bit quickly through this. But we now need to integrate x cosine x, so let u equal x, dv equal cosine x dx. Then du equals dx, v equals sine x. So we have the integral of x squared sine x dx equals negative x squared cosine x plus 2 times this integral x cosine x, but that equals x sine x minus the integral of sine x dx. Almost done. We get, distribute the 2. The integral of sine x is negative cosine x. So we have a negative coming from the integral, a negative coming from here. So we're going to get plus. We have this 2, so plus 2. And then the integral of sine x, as we said, was negative cosine x, but we already dealt with the negative sign. And there you go. So sometimes you'll have to use integration by parts multiple times. And notice how many times we used it. So scrolling, scrolling, scrolling. We have x squared, the thing that terminates. It no longer has a variable after differentiating it twice. And we use integration by parts once, and then we use integration by parts twice. So generally speaking, if you have something that terminates, you're going to have to use integration by parts as many times as it takes until it is no longer, until that thing that terminates no longer has a variable. So that's great, but imagine if I wanted to have you integrate x to the 10th sine x. You'd be here forever. So I'm going to teach you a slightly different method for doing integration by parts. And really, it's the same method. It's just going to be written differently. This method is known as the tabular method. Which is just a way to represent integration by parts multiple times. So how do you do this? You draw a table, hence the tabular method, with u and dv. So I'm going to have that, oh, dogs are barking again. I'm going to have that going over here. We have u, that's not a u and dv. And we're going to do the example we did before, x squared sine x. So u we said was x squared, dv we said was sine x. You then differentiate u until it terminates. And integrate dv that many times. Okay, so differentiate u, you get 2x, 2, 0. Integrate sine that many times, you get negative cosine x, negative sine x, and then cosine x. Going to use colors. You add alternating signs. So you're going to start with a plus in front of your first u, and then you alternate. And then you multiply diagonally. And add the last row. Don't forget the signs that we just wrote down. Okay, so what does that look like? That looks like you're multiplying this, multiplying this, multiplying this, and then adding that. So what are we doing here? Doing this this arrow. So when you multiply these two, you're doing u times v. So you're doing that uv, and then this minus sign is the minus the next integral, which will be u times v. And then you'd subtract off the next integral, but we already have a negative sign, hence we have this plus, and then you'd have u times v, and so on. So doing this, you would get x positive. You have positive x squared. Let's not do it. Hold on one sec. Erase. We have the integral of x squared sine x dx equals positive x squared times negative cosine x, which comes from number 1, minus 2x times negative sine x, which comes from number 2, plus 2 times cosine x, which comes from number 3. And then you multiply the last row. Minus 0. And then plus C. Where the last row number 0 comes from number 4. Okay, so that's the tabular method. So let's see that in action as an example we have not seen before. So example, use the tabular method to evaluate the integral of x cubed e to the x dx. So looking at this, we expect, since x cubed will take 3 times before it terminates, we expect to have to integrate by parts 3 times, which would take a while. But I'm going to let you guys do this one. Why don't you pause it and try this, and then when you're done, come back and verify that you did it correctly. Okay, so first we have to determine what do we want u to equal. So according to Liotti, we let u equal x cubed. So we have u dv x cubed 3x squared 6x, differentiate u 6 and then 0. What is left over? You have e to the x left over. Integrate that, and the dogs are barking again. And the nice thing is e to the x just is always going to be e to the x when you integrate. Add your signs, plus, minus, plus, minus, plus. And then multiply diagonally. So reading this off, you have the integral of x cubed e to the x dx is x cubed e to the x minus 3x squared e to the x plus 6x e to the x minus 6 e to the x plus 0 and then plus c. See, much faster than trying to write out the integration by parts 3 times. Okay, so everything we've done so far with integration by parts has been with indefinite integrals. But you can use integration by parts on definite integrals as long as you remember one thing. Oh, my Apple Pencil is going to die. Be sure to evaluate uv also. So what do I mean by that? The integral from a to b of u dv, so writing out the integration by parts formula, you have uv minus the integral from a to b of v du. So make sure to transfer these limits over to your new integral. But be sure that you also translate those limits to this u times v. So make sure to evaluate u times v from a to b. So example. Find the area of the region bounded by the curve y equals x e to the negative x, and the x-axis from x equals 0 to x equals 4. So I say solution, and we are going to solve this, but I'm just going to put the graph in the solution. So the graph looks something like this. Ah, beautiful. So from x equals 0 to x equals 4, we are wanting to find this area. So the area bounded by y is given by, we know that the area under a curve is just the integral. That's going to be the integral of y, which is x e to the negative x dx. And we only want to go from x equals 0 to x equals 4. So that's the integral from 0 to 4. We have a product of two functions, so we're going to use integration by parts. We use integration by parts. In this case, again, similar to the last example, we're going to let u equal x and dv equal e to the negative x. Differentiate u, you get x, 1, 0. Integrate e to the negative x. You get negative e to the negative x, and then e to the x. Kind of running out of space. I think I made it work. Add your signs, plus, minus, plus, and then multiply diagonally. So this integral is negative x e to the negative x, evaluated from 0 to 4, minus e to the x, evaluated from 0 to 4, and then plus 0. We don't have plus c because this is a definite integral. Okay, so the first term will be negative 4 e to the negative 4 minus negative 0 e to the negative 0, which is just 0. And then minus e to the 4 minus e to the 0. Sorry, I forgot a negative sign. Let's do it in green. When I integrated dv, the last one should have a negative sign. So it should be negative sign there, negative sign there. All right, we have negative 4 e to the negative 4, and then minus another one. So that's negative 5 e to the negative 5. And then we have minus a minus 1, so plus 1. And so I made another mistake right there. That should be 4. Whew. And there you go. So key thing when you do integration by parts on definite integrals, don't forget your new limits of integration everywhere. And it's not too hard when using the tabular method, but if you didn't use the tabular method, it's a little bit harder. Or it's easier to forget. Okay. We do one last example for this section. And we do this example to illustrate how to deal with integrals that neither of the terms are ever going to terminate. So in particular, that means you can't find a u that terminates. This is a very, very popular example for calculus, Calc 2. It's almost guaranteed that you would get one on an exam in some way, shape, or form. So, evaluate the integral e to the x sine x dx. So first off, I'm going to label this integral I, so I don't have to keep writing this integral again. We have a product of two functions, so we use integration by parts. By Liotti, so we have L, I, A, we do have trigs, and we do have exponents. So trigs come first, so we're going to let u equal the trig function, sine x, and let dv equal everything else, e to the x dx. Differentiate u, you get cosine x, integrate dv, and you just get e to the x back. Okay, then our integral is uv, e to the x, sine x, minus the integral of v du, which is e to the x cosine x dx. Okay, repeat this process because again we have a function here that is a product of two functions, e to the x cosine x. So we repeat. In this case, we're going to let u equal cosine x and dv equal e to the x dx. So our integral I is e to the x sine x minus uv, which is in this case e to the x cosine x, minus the integral of v du, which is negative e to the x sine x, so that's plus this integral e to the x sine x dx. Okay, distribute this negative sign from the first integration by parts, and you get e to the x times, oh, that's not how you spell that, sine x minus cosine x, minus the integral of e to the x sine x dx. Okay, what now? Well, we're back where we started. We have this integral again. Well, that's actually really good. Oh, I need a new page. So we can write this as e to the x times sine x minus cosine x minus I, the integral that we want. Add this integral over, and you get 2I equals e to the x times sine x minus cosine x. And we'll add a plus c now at this point. And then just divide by 2. And you got that your integral equals e to the x divided by 2 times sine x minus cosine x plus c. So this only works if you get an integral that repeats itself when you do integration by parts. So notice when we got to this point, we got back to the original integral. Looking back at the very first example that we did, I said, notice that the choice of u matters. I'm going to scroll now. Scroll. Notice that the choice of u matters. We let u equal cosine x and dv equal x dx. And when you did that, you got your integral x cosine x turned into an integral of x squared sine x. Do it again, and you would get something that looks like, not entirely sure, integral x cubed cosine x dx with some constant k out front. And the cosine repeats because we got cosine x back, but this isn't the same integral because we have an x versus an x cubed. So it only works if, this method only works if you the integral completely recycles itself or repeats itself. And that's only true if neither of the terms are going to ever terminate when you differentiate them, because in this case x does terminate.